Morning, everyone. B Flat here. Today is February 21st, 2026, and going to continue with my analysis of refraction. Um, how it is being misrepresented by those who counter individuals who believe that the Earth is flat based on their observations. They claim that we reject the science, the physics of refraction, and because we're refraction deniers or from its principle deniers or denier, we are wrong and they are right because they understand refraction. Well, who are they? I don't believe we're arguing or debating against scientists or people who are representing the science correctly, the physics. So let's just do some quick visualizations that I found on YouTube. The first one being refraction due to waves slowing down. Okay, this would be the classic example, Snell's law. You would have your air to water, and you have a wavefront that is going to enter at an angle of incidence and leave at an angle of refraction. Now, I know immediately this community of computer programmers, we'll get right to the point of saying that. You have individuals who are educated in ray tracing and visualizations, and we'll touch on that more, but these are the people who are going to be responding to this, or the people who cannot judge the ray tracing programs properly as far as their real world applications, or if their simulations reflect what really is going on in the real world.
First encounters a piece of glass, one side is slowed down before the other, forcing the wave front to change direction. This bending of light, whether in glass, water, or any other transparent material, is called refraction.
So we can stop this one right here. That's what refraction is. So I created this a while back. Basically, we have just a line drawing of what we just witnessed in regard to refraction. Now, again, as the community of computer programmers are going to put out, is that you cannot apply Snell's law, the formulas for Snell's law, to an area of medium that doesn't have hard borders. It is not fixed. You are going to have light that is going to progress into a denser medium. Again, I think I've covered this ample times. It still has to enter into a medium where the IOR, the index of optical refraction, is changing. And that will be in our atmosphere, the vertical area from space to the individual who is observing it, wherever they're observing it within our atmosphere. This path can progressively refract if the change in medium is progressively increasing. Starting out here, vacuum of space, IOR of 1, and gradually increasing all the way down to get to the value of, I believe it's 1.00003. It's close around there, but it does change over distance. So distributing that change over a path would require the use of iaconical equation, I believe it's called. It's a calculus expansion off of Fermat's principle of least time. The path that light takes in the least amount of time in order to get to the observer. Okay, we're not going to argue with that. So let's take a look at this at another video animation of how it applies from astronomical observations. I turned the sound off because it was annoying. Now, we have individuals who will say our atmosphere is not layered. Yeah, officially it's not a structured, hard boundary layered surface. It progressively refracts down through. It progressively gets, for the most part, denser. In the lowest atmosphere, where the sun warms the surface of our Earth and that energy radiates back up through, this area really is called, it's diurnal in nature. Twice a day, it alternates, flips back around, and the density changes dramatically in that layer. It does not follow the generalization that, from here up, you get outside of or above the height of where the surface of our world is affecting that lower atmosphere, then there is a generalized trending into less dense atmosphere. It starts at a point, though. It's not down here. You cannot generalize the lower area. You can generalize, the air above it. So I'll continue with the video here. We can see that an actual path of light from the star to the individual results in a perceived change in where that star actually is, or where an object on the surface of our world would appear to be from an observer due to refraction. We are judging where something is, or interpreting where something is, or surveying where something is, based on how that light makes it to us. So while I've been debating individuals lately, an individual threw out the term iconal equation for optics. And again, this would be what anyone grinding lenses, anyone in the optics field would take, and they would apply a mathematical equation so that they could figure out what they would need to do to achieve a desired goal. You would have a thickness of the lens, which would be the length of the light's path through the lens, and you would have to introduce either angling of the surface, convex, concave, optical lens shapes, in order to redirect the light for the desired goal. You can also add internal variations in optical density along with the lenses, the shape of the lenses, to produce different effects. And I'm sure there are real scientists out there, or physics majors, that can take and calculate and know exactly how to structure the medium that they need to project or view light through in order to achieve the goal that they're trying to achieve. Okay, so common applications would be ray tracing. I just brought up ray tracing. This is where we have a problem, and I will explain that problem as we go. Seismology, numerical models. This basically comes down to how this formula, this calculus formula, is utilized. Is it being utilized properly? We know that people who make telescopes or magnifying glasses, any optics, okay, we know they're using it correctly. So how about the ray tracers? We can really get into that now. I'm going to bring up a Word document here which covers some of the individuals I've been having the latter conversations with. And yes, I am engaging Walter Bislin in conversation. Walter wrote, "It does not require a curved atmosphere to bend horizontal light beams toward the denser part, if that is what you mean. I've never mentioned anything about a curved atmosphere. The only thing I've mentioned is that any path of light that is traveling from one location to another is either going to experience a change in density along that path, or it's not. If it changes along that path, it will refract. And it can either refract on a single bend or a progressive bend. Again, we will get back to the derivative. If light is traveling and it hits a small pocket of change, slight, it can refract at an angle. If light hits a progressive section of optical density change, then it will continue to bend based on an iconical equation. It will bend in something that's similar to a curve. But upon exiting that duration of change, entering that duration of change in IOR, that light was moving in a straight path, and once it hits a stable atmosphere of no change, it will continue in a straight path. So, if we take light traveling, first, this is structured just like our atmosphere for descriptive purposes. Okay, our atmosphere stacks vertically. These individuals will talk about the vertical lapse rate, or the lapse rate, the vertical rate of change, the vertical gradient. Okay, no one is disagreeing that the air well above the surface of our world is less optically dense than the air at the surface. Okay, but the rate of change would be light moving down through that rate of change, not moving perpendicular to it or parallel with the supposed layers. And our atmosphere is not that defined as being rigid in, a very specific altitude has a very specific IOR. We're diurnal, we're transitional through the day. You know, our weather moves in and out. It moves across us. We experience changes based on wind pattern, cloud cover, the intensity of the sun, whether the sun is above us or further away. I mean, between the Tropic of Cancer and the Tropic of Capricorn, the angle of the sun to us really warms us a bit differently. But that is changing. And for the most part, our changes will be more recognized across a vertical rate of change than they will across the horizontal. The horizontal, there will be changes, but they will not be based on a trending across the distance. The trending across the distance is an important thing to remember when I get to that point. So let's get back into the Word document. So yes, the bending of light has nothing to do with layers of different densities. Again, our atmosphere is described as layers. It's stacked in the vertical, and get over the whole layer aspect. Okay, light would bend due to a smooth change in density. He's even saying vertical here. It is relative to a path of light traveling in vertical or across the vertical. Horizontal is 90 degrees to that. Causing the refractive index gradient. Again, gradient is an interesting word to different people in this equation, but if we are going to, as I think Billy Bowden says, the logical assumption of the gradient is the gradual change over distance. Some people say the gradient is one point somewhere in our atmosphere that we can measure and apply that one little measurement to the formulas that Wally over here has put in his program and exploit it from there, because it is exploited. So even if light starts perfectly horizontal, it gets bent by the vertical density gradient towards the denser part of the atmosphere. Wrong. Okay, you must not apply Snell's law if you have only a single density gradient, a continuous change in density with increasing altitude. I think I just covered that again in the umpteenth time in all the descriptions I've put out there. Okay, you do not exclude Snell's law. You expand on it with principles and calculus when appropriate. Again, when appropriate. When it's justified. So yes, Wikipedia. Snell's law is a formula used to describe the relationship between the angles of incidence and refraction when referencing light or other ways passing through a boundary. Boundary being the important. Between two different isotropic media. Okay? The atmosphere isn't isotropic. But we do not disregard an angle of incidence and the norm. So yes, you would have to apply Fermat's principle, okay, and eventually getting around to that iconal equation. Yes, you would. But you have to justify the medium is appropriate for you to apply it. You cannot just grab a measurement from anywhere and assume that it is continuous across all paths across the atmosphere. Okay, that is an incorrect thought process. Our atmosphere does not structure indefinitely the way you are applying the math to. You might find a short distance that behaves for your equation, but it is not without duration. I'm going to jump over to Wally's website here. So this program basically works by supposing a curved path of light based on a specific path of change, whether it's a meter or it really doesn't clarify the overall distance or duration of change that the calculations are made. In fact, when it's all said and done, that's really irrelevant. Okay, if someone is trying to justify a curved path of light as being refraction, they're justifying that that path of light is limitless as far as its arc length. Again, I just think I've covered this, that our atmosphere is not structured across the horizontal path for that to be even considered possible. The lowest of probabilities that a weather phenomena could move in that makes that happen for you does not warrant your model of refraction being the standard, your program being something that works off of a standard. So what does this program do? Once it has sold someone on the belief that light in our world, our real world, what we view, what we experience, always moves in a curved path, then all is lost. I reject that in full. I know when it's appropriate and when it's not appropriate. And this is not appropriate. So what do these people have to do at this point in time? You know, if we were looking at, BLMSB, the Black Swan, an observer height of 1 foot, target distance of 9.21 miles, and we're going to do a target size of 1 foot because we're under that if we're observing the water's surface in the distance, which it was observed beyond where the legs of the gas rig hit the water. Oh, and yes, there's the bendy cranes. We know about the bendy cranes. You know, talk about the bendy cranes. But let's also talk about that that's an industrial platform. And during the video, it's captured that it is in the process of burning off waste gas or generating power or whatever it was doing, because between the flame boom that moves off to the left and the crane that's centered, I've pointed out the exhaust pipe, as well as the fact that you can see, you know, the heat and the smoke coming out of that emission device. So it is not part of the standard atmospheric profile. It's an industrial platform. You can look across anything that is radiating heat, and it will produce a localized refractive distortion. It's heat distortion. It's a form of refraction. Okay, but it's not relevant to where the legs hit the surface of the water. And at this point, we should have had, there should have been 42 feet of that rig that was obstructed by an earth bulge. So what do you have to do? Well, you're not entering in anything of specific value across that path. In 1 foot of air column, how much progressive change in IOR can you expect? Well, the program requires you to change the curvature, the real radius of the Earth, or what they claim the globe to be, the apparent radius. If we're at zero refraction, that is what they're trying to sell. And the method of spreading out that refraction across the complete 9.21 miles requires them to assume the max amount of distortion required to make the apparent radius, oh hell, how many times more is that? 1,000 times greater? The radius is 1,000, would have to appear to be 1,000 times greater to assume this. Okay, so they're not telling you what the environment is. They're telling you what the program requires. The most extreme amount of refraction is what this program requires to explain the observation, based on the calculations and the misapplication of the mathematical physics behind what's going on. It's not a optical specialist grinding a half-inch thick lens using the formulas properly in order to achieve a goal, or stacking lenses with distances across a telescope to achieve the desired goal. This is a computer programmer using ray tracing and formulas that are derived from real physics inappropriately, incorrectly, based on what our world is. So we'll continue here. Gradient index optical fibers would not work with Snell's law. Never said they did. But our world is not gradient index optical fibers. So using calculus, great, we can derive things from principles and calculus if they are applied in a medium that justifies applying the calculus and Fermat's principle correctly. So I don't care about your formulas for curvature. Okay? Again, you're pulling data from anywhere, irrelevant to the paths that I'm discussing. So, no, I am not doubting the equation to be correct. I'm doubting the application, the data that feeds it, how you are applying all of this to your program. And I reject your program. Full stop. So, we just talked about the black swan. Great, yes. You need to assume as much refraction as possible to reproduce the black swan. Assume. I just covered that. So yes, I will call it BS as much as I like. And the physics have been known for centuries. What I'm telling you is you don't have a clue as to how to apply the physics properly. So now we get into another individual, Billy Bowden, 7079. There's a universally accepted scientific explanation for why light initially traveling perpendicular to a density gradient will bend down. In the simplest term, light propagates as a wave, and if the bottom part of the wave is traveling through a denser medium, then the top, the wavefront, will tilt. Okay, well, the first animation that I showed a wave front, the lower part of the wavefront, entering a denser medium at an angle and refracting into it. Okay, that was explained in the animation. It can be expanded on more. With the iconical equations. If the light continues to enter into a denser and denser and denser and denser and denser medium, which really can only exist in a downward path into our atmosphere, not horizontal. The bottom part of the wavefront, if it's moving in a denser medium, it's traveling slightly slower than the little bit above that and the little bit above that, but it's not hitting a change at an angle of incidence. It is not bound where the wavefront is hand in hand, and one little drag on one side is going to pull everything into the ditch. No, that is an illogical thought process. One part of the wave may move slightly slower than the other. Probably not even measurable based on how little change there is between inch by inch of our atmosphere as you move up or down. So no, this stupidity that you're bringing is truly not science. This is something that, again, is coming up from the wishful thinking of simulation programmers, people writing equations. So, of course, Billy now will throw out there's a robust classical explanation for involving phase lag from dipole oscillators and quantum explanation, geometric explanation using secondary waves and blah, 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 blah. You want to know something? It's not our atmosphere. Our atmosphere is not a dipole oscillator. We're not looking for quantum explanations for something, an observation over 10 miles. Oh, and they predict something. And their prediction based on your misappropriation or your misappropriation of these stories makes you correct? Hell no. Give it up already. Just give it up. It is also the same physics you'd be using if you were designing a gradient refractive index lens. Hey, great. I've already covered that, didn't I? Gradient refractive index lenses. One, which the material was manufactured to have the increasing density as light would progress through it. And then also grinding it into a lens. Another way of redirecting light. This physics isn't a guess. Of course it's not a guess. It's applied in theory and practice properly, unlike a ray tracing program, which has no limits if you tell a program light is moving in a radius, it will do that indefinitely. Because it does not require anything in the real world. It's virtual. It's an assumed path. Assumed. It doesn't exist in the real world, naturally. Just because you can simulate it in a computer based on an equation you misapply, and you're not misapplying it, you're applying it to a virtual world. That's different than the real world. Your virtual world is different than the real world. Your techniques as to how to explain the real world from your virtual presentation are wrong. So, my response to old Billy Boy was to point me to book and chapter and page of the literature that states / validates your so-called universally accepted explanation. Because when I look, I don't find anything. Okay? None of these individuals seem to stray from the basics of Snell's law that requires an angle of incidence into change in IOR value. They expand on calculations, limitations of Snell's law They expand on calculational limitations of Snell laws to utilize calculus for the progressive change in IOR. Progressive change in IOR. Density change over a grade. Gradient. Rate of change. Direction of change. Overall distance of change in the medium. So yes, the BS of the light slightly traveling, I just covered that. People can read it here. So the balance of this really circles back to what I had said earlier about the iconical equations. These individuals, these computer programmers, with knowledge of an iconical equation that they can play into their simulated world, and through arrogance and ignorance, and probably coming from the gaming community, engage people with rational thought processes and understanding of science in a playful way because they think they're special, they think they're smart. I could go back through countless of people that I talked to that I question what age they were for the juvenile method that they put in place. You're wrong because here's a name. These people never explain exactly what's going on outside of the mathematical equations that they think they can collect and put together that says, here, argue with the math. They're not going to justify it because they don't understand anything beyond the math. Our atmosphere for terrestrial observations is never, or rarely if ever is probably the best word because you can never say never. I would say they probably have 1 in a trillion chance of pulling it off on a day-to-day basis. Our world isn't structured like that. So your Earth calculations are dismissible. You don't understand Earth. You don't understand the atmosphere. You understand a mathematical equation, and you don't apply real Earth data to that. That justifies what you try to do across the distances you try to do it. And I believe this has gone far too long. For anybody who's made it this far, there's other videos that I have done which kind of step everything into this process, but I hope I've covered everything as clearly as I could possibly cover it, for those who may have just stumbled upon this. And I'm willing to answer questions from anyone with a true interest in clarifying something, but I'm getting real tired of the same computer programming 2-bit twits, from Wally's World or Billy Boy Bowden's world, truly not understanding what refraction is. I don't deny refraction. I don't deny Fermat's principle. I don't deny the calculus. Okay? Don't deny any of that, if it's applied appropriately. And clearly, it's applied with the utmost arrogance from people who know nothing about our atmosphere. Thank you.